So last time we went through a worked example of a recurrence relation of order 2 with constant coefficients. First of all, we solved the homogeneous equation, and then the extra term, which here is called C0 of n, actually involved a solution of that homogeneous equation. So we had to multiply the sort of normal guess by n. Then we put everything together and solved the initial conditions. So what I want to do in this segment is just to explain the technique a little bit more theoretically and say a bit more about the sort of particular solutions you need to guess or try for different instances of this extra term that one has here. So I'm going to start with slightly more general recurrence relation, a so-called linear recurrence relation. For simplicity, I'm going to stick to order 2, which means that an depends on just 2 preceding terms of the sequence, so it's of order 2. Now, most of the time we'll be dealing with the situation in which these two functions, C1 and C2, are actually constants. So those are the so-called recurrence relations with constant coefficients. But typically the extra term C0 of n will not be constant. But in the definition of a linear recurrence relation, we don't demand that C1 and C2 be constant. They can be any functions of n. The important thing is we've got this sort of linearity in the sense we have this sort of linear combination here. So that's the sort of equation I want to consider now at a theoretical level. And as before, even if C1 and C2 are not constants, we ought to first of all look at the associated homogeneous recurrence relation. So that simply means that we forget the last extra term. So here's the associated homogeneous equation, which I denote by H. I've slightly rearranged it to put the sequences on the left-hand side, but you can see all I've done is I've just essentially to go from NH to H, I've just eliminated the extra term. So it's a good idea to always get into the habit of putting the terms with C1 and C2 on the left-hand side, then you won't make a mistake when you write down the associated polynomial equation. But anyway, let me give you some theoretical results about this sort of equation, whether or not C1 and C2 are constants or functions of n. So I've put together some facts in a proposition. Here are the first 2 facts. So if we have 2 distinct solutions of the homogeneous equation, then because it's a homogeneous equation, because we do have 0 on the right-hand side, we can take any linear combination of those solutions with constant coefficients, capital A and capital B, and that linear combination here, written here as a sequence, will actually solve the homogeneous equation as well. I mean, this should all be familiar to you from if you've done a similar thing in ordinary differential equations. It's completely analogous. You can have non-homogeneous differential equations, you look at the corresponding homogeneous equation and so on. So this is a linearity property, the ability to combine solutions in linear combinations will always be true in the homogeneous setting. And it should be easy to understand why this is true, because you can just take this equation. We've also got Bn satisfies it. So you copy out the same thing. You can just essentially multiply the first equation by capital A and the second equation by capital B and add them together, and you'll see that will also be a solution. Now it turns out that if we have if the equation is of genuine order 2, so that would require C2 in particular to be non-zero, assuming this is not identically 0, then we do have order 2, and we will in that situation be able to find 2 independent solutions of the homogeneous equation. So independent or linearly independent simply means I'm treating the sequences as if they were sort of infinite vectors, and I'm saying those vectors are linearly independent. All that means is that it's not the case that all the terms of one sequence are the same multiple of all the terms of the other sequence. If we have one solution an and we multiply every single term by 2, then obviously that's also going to be a solution, but it's essentially the same solution of the recurrence relation. So if we have independent solutions, it means that the second sequence is not just a constant multiple of the first sequence. In general, if you have a recurrence relation of higher order, and you may occasionally see one of, say, order 3, then that you would expect 3 independent solutions of the homogeneous equation, and so on. And the fact that in this case we have 2 independent solutions is related to the fact that we have these 2 constants a and b, because if we have to solve a homogeneous equation with some initial conditions, 2 initial conditions, those initial conditions we can use them to determine capital A and capital B, assuming that the 2 solutions here are linearly independent. Okay, now the third fact, so that's really the situation for the homogeneous equation. The third fact it tells us something we've already done, actually. It tells us how to solve the original non-homogeneous equation. Namely, we often try and guess or find just one solution, call it Pn, it's a sequence, that solves the non-homogeneous equation, P for particular, so we have one particular solution maybe we're able to find quite easily that solves the non-homogeneous equation. Typically we're not just interested in a single solution because we want to satisfy initial conditions, so we need the general solution of the original non-homogeneous equation, and we can easily get that by adding the general solution of the homogeneous equation. So that's what we're doing here. So this is any solution of this third fact is telling us that any solution of the non-homogeneous equation will have this form for suitable constants capital A and capital B. So another way of saying that is that any other particular solution will differ from our first one, Pn, by adding a linear combination of the 2 solutions we have of the homogeneous equation. Okay, so that is the situation, and we essentially use these facts in the worked example I did before. We had to find a particular solution to give a constant term, but we couldn't use a constant because that solved the homogeneous equation. So for a particular solution, we looked for a constant times n, and we found it. Okay, so that's the situation in general, and let me go on now and let's go through another worked example. Okay, so it's just another worked example, so I'm going to just go through in a similar vein, but I'm going to give you the strategy more formally that essentially repeats what I said in the last video. So in this worked example, let's just look at it before I put any more text on screen. So here we have obviously constant coefficients because C1 and C2 are just constants, and I've been careful and put those on the left-hand side of the equation. And the extra term that before in the previous slide I called C0 as a function of n, C0 of n, in this case C0 is meant to be C, is just 2 to the power n. And when you see that, before we look at the initial conditions, the first thing that you should ask yourself, is 2 to the power n a solution of the homogeneous equation? If we forget about the right-hand side and replace 2 to the n by 0, is 2 to the n a solution of the homogeneous equation? And you see very quickly here it's not, because the roots are not 2. I'll tell you what, I'll write it down in a moment, but you should be able to just look at this and sort of write down, let's just scribble down here, the associated quadratic equation is x squared minus 8x plus 15. This is for the homogeneous equation, in which we've sort of put a 0 here. This is equal to 0, or sometimes I use lambda. I think in the notes I use lambda. Same difference, of course. That equation, that quadratic equation, you can spot its roots because it factorizes into lambda minus 3 times lambda minus 5. So the roots are 3 and 5. So that tells us that our independent solutions are 3 to the n and 5 to the n. Okay, and 2 to the n is not, therefore, a solution of the homogeneous equation. Okay, so in some sense this example should be a bit easier than the previous one, provided we can guess a solution for the particular solution, which I'll show you is quite easy in this case. So let me get rid of this, and let me go through formally and just write down formally the strategy to solve this type of equation. So here's the strategy, and we've already applied this. I've just written it out more formally. You'll find this also in the lecture notes, although maybe I separated the homogeneous and the non-homogeneous cases, I forget. Anyway, what do we have to do? We have to first of all look at the homogeneous equation and find its roots. We've already done that. The roots are 3 and 5. So here lambda 1, it doesn't matter which is which, of course. We could take lambda 1 to be 3 and lambda 2 to be 5 in this case. So, well, it's a bit problematic if the roots are repeated. I'll explain that on the next slide. But assuming they're not repeated, and here they're not, they're distinct, we know that the general solution is a combination of the two solutions I mentioned already. So constant times 3 to the power n plus a constant times 5 to the power n. Now the bit that can be a bit tricky, we have to guess the form of a particular solution of the non-homogeneous equation. Well, I'm going to type this out in a moment, but let me just do it by hand now. You see, the extra term, I sometimes call it the forcing term, thinking of differential equations. The extra term in this case is 2 to the n. That's not a solution of the homogeneous equation. So actually what we can do here is we can guess that Pn, we should be able to take some constant, some other constant, and call it alpha, times 2 to the power n. In fact, we will be able to solve the non-homogeneous equation. We will be able to find a particular solution which has this form. And I'll do that in a moment. It would have been more tricky had 2 been a root. In that case, we'd have had to multiply our guess here by n, as we did actually in the previous video. Anyway, in a moment, we're going to find that constant alpha. Once we've got the constant alpha, we know what the particular solution is, and so we can just add it to the general solution of our homogeneous equation and then find the arbitrary constants a and b to satisfy the initial conditions, so they'll no longer be arbitrary. Okay, so these constants are handled in a slightly different way. The important thing is to find the constant immediately for our particular solution. Okay, so that's the way you solve all these equations with constant coefficients, and the only tricky thing is guessing the particular solution, and there are various complications. There are complications if the forcing term is a solution of the homogeneous equation. Here it's not, and there are complications if your roots are repeated. Here they're not. Or the roots could even be complex, and there's an example in the lecture notes of what happens if the roots are complex. But if you're interested in that situation, let me give you a very simple example of a recurrence relation in which the corresponding quadratic has complex roots. Let me just take an plus an minus 2 is equal to 0. And you know, you can just try and solve that yourself. What is the, you can apply the technique, it will work. You just need complex roots. But you can also sort of almost guess how you would solve that equation. and find, for example, a particular solution of this recurrence relation. Okay, let me now then solve in detail the worked example at the top. Type out more neatly the solution. So let's do this step by step. So as I said before, we work out the associated polynomial. We've already done all that, so that line's been done. The general solution we know is of the homogeneous equation is a constant times 3 to the n plus another constant times 5 to the n. Now, as I said before, we're going to guess a constant times 2 to the n for our particular solution, and it's easy to find what alpha is, because when we just substitute Pn in place of An, so we just substitute in that. When I say substitute in, I mean we replace An by Pn. So we just put alpha 2 to the n here. And what we're going to get, what I've done here to get this equation is I've substituted in and I've divided both sides by 2 to the n minus 2. So I'm actually left with an extra 2 squared here, which is a 4 here, an extra 2 here. So I get a sort of extra 4 here, an extra 2 here, and nothing here. So that's why I get these coefficients 4, minus 16, 15, and then if I divide by 2 to the n minus 2, I'm left with a 4 there. So if you put that together, you discover that alpha must be 4 over 3. Okay, so we've got a particular solution, 4 over 3 times 2 to the n. So let's put everything together then. And so we have this. We now have this general solution of the original non-homogeneous equation. That's the general solution. So we just have to satisfy the initial conditions, and I've made them easy actually by making them both equal to 4 over 3. So you see that if you take n to be 0 here, you get a plus b plus 4 over 3 is equal to 4 over 3, so that simplifies to a plus b is 0. And when you put n is equal to 1 here, you're going to get 3a plus 5b plus 4 over 3 times 2, that's 8 over 3, is equal to 4 over 3, so you get a minus 4 over 3 on the right hand side. So you can then solve very quickly for a and b. B is minus a, and so you're going to get, I think a is 2/3. Okay, so a is 2/3, b is minus 2/3, and now we've solved the original equation. So we have that the full solution is 2/3 3 to the n minus 2/3 5 to the n, and then 4 over 3 times 2 to the n, and I just rearranged that slightly by taking a common factor of 2/3 out, so that instead of 2 to the n here, I've converted the 2 to the n into 2 to the n plus 1. Which reminds me to say something. I mean, I've written here that the general solution is a times 3 to the n. I could have equally well have said a, or different a, let's call it a prime, times 3 to the n plus 1, because changing the power here, it's just changing the constant. So the fact I put 3 to the n, I could have called that 3 to the n plus 1 if it were convenient to do so. Okay. So now I want to, in the remaining minutes, I just want to tell you how you make guesses or make intelligent guesses for particular solutions. So, well, before I do that, let me just point out that if we have a recurrence relation of higher order, unlikely I think you'll meet anything worse than a cubic, case 3, but if we did have one in which we have an that depends upon a number of previous terms in the sequence, we'd get a quadratic equation with more than 2 roots, maybe k roots if it's order k. So the same technique will work. So, well, let's come all at once anyway. So the point is this, that if we have a repeated root, then in order to get independent solutions, we have to start multiplying by n or even powers of n. So if a root is repeated r times, then we need to we will need r independent solutions to take account of that. So we need to take the first sort of obvious solution, which is the root to the power n, and multiply that by powers of n up to n to the r minus 1. But in practice, we only normally come across this in the quadratic case. So in the quadratic case, the worst that could happen is one repeated root, so one double root, in which case you take your obvious solution and the independent solution will be n times that. So that's the important thing to know. And we already saw an example of that when lambda was 1. Okay, so here's my table of sort of guessing particular solutions. So at the top of the table I've said, so here is the extra term that converts the homogeneous equation to the non-homogeneous equation. And in my first example, I've taken the example we've just done. So if the extra term is 2 to the n, provided that 2 is not a root of the homogeneous equation, you just try a constant times 2 to the n. That's what we just did. Now, a similar situation would be if on the right-hand side we just have 1 to the power n, which is just 1, or any constant, like 100, then we would just try a constant. Probably it's going to be a different constant to get 100 on the right-hand side. It's no good just shoving alpha to be 100, but some constant should work, provided 1 is not a solution, provided a constant is not a solution of the homogeneous equation. If it were, as it was before, one would have to multiply by n. Then getting a little bit more complicated, you see these exponential terms are somehow easier. If you see on the right-hand side n, or 3n, or 100n, it's not good enough just to multiply to take a constant times n. You might be tempted just to take a constant times n as your particular solution, but that typically will not work. You have to take in fact, a polynomial of the same degree. Well, here the degree is only 1, but we have to take a polynomial of degree 1. That means we need 2 constants to be determined. So we try alpha n plus beta, and have to find both alpha and beta. If you just set beta equal to 0, typically that will not work. So similarly, if you have a polynomial in n, so it might be n squared, for example, it's no good just trying a constant times n squared. You have to try alpha n squared plus beta n plus gamma. And if putting these two things together, if we have a polynomial times an exponential term, as is the case in this last example, then you have to try a polynomial of the same degree. So it won't be enough just to put alpha n squared. You're going to have to add on these extra terms. So here you'll get 3 constants. Multiply all that by the exponential term and determine alpha, beta and gamma. And that will only work provided 3 is not a root of the homogeneous equation, which actually it was in our last example. So if it is a root, you would have to multiply everything by n again. Because the gamma term, if 3 to the n were a solution of the homogeneous equation, this gamma term would be useless. So you have to multiply everything by n. So you'd actually have alpha n cubed plus beta n squared plus gamma n. But that's what I've written is okay if 3 is not a root of the homogeneous equation. So the last remark then, shall type in, is if on the right-hand side, if any term on the right-hand side, if any of these terms like this, like this one, or this one, or this one, are solutions of the homogeneous equation, then, well, these two together I meant, then you have to multiply everything on the right-hand side by n. And if you had a repeated root of the homogeneous equation and a solution of the homogeneous equation visible, you'd have to multiply everything by n squared. That's about as complicated as it's going to get. I'll stop there. You need lots of practice on these particular solutions. Bye.